Funding for this program was provided by the Annenberg CPB Project.
In the 18th century, electricity was just a curiosity. But in the 19th century, it became one of the most important tools, not only of science, but of industry. And the crucial invention that caused that transformation was made just in the year 1800 by Alessandro Volta, and it was, of course, the electric battery. I wanted to bring in a car battery to show you this morning, but when I went to the automobile showroom, it turned out that all they had was a lemon. So I thought I'd make a battery for you out of a lemon. Now, if we're going to use this as a battery, of course we have to have electrodes to take the electricity out with. So I'll just put in a zinc nail, like that, and a copper nail, like that. Now, to show you that this really is a battery, I'm going to connect it to that galvanometer, or digital voltmeter, right over there. Now watch. When I connect it, you'll see that it will read just a little bit under 1 volt. The volt, incidentally, was named after Alessandro Giuseppe Antonio Anastasio Volta. Of course, his full name was a little too long to use, so they only used his last name, and even that was too long, so they shortened it to Volt. And by the way, the galvanometer was named after Giuseppe Galvani. And those two, Alessandro Volta and Giuseppe Galvani, are the principal characters in the story that we want to tell today. In any case, it would be nice to be able to do something more with our lemon battery than just connect the voltmeter across it. For example, it would be nice to be able to run this little electric motor with it. I can try to do that by connecting the electric motor to my battery like this. But if I do that and then close the switch, absolutely nothing happens. The reason for that is that although the lemon really is a battery, it's not a very good battery. It wasn't designed to be a battery. It was designed to be a lemon. What that means is that although current runs out of the lemon, it doesn't run out fast enough to run the motor. It runs out very, very slowly. But there's a cure for that. All I have to do is to collect it, store it up. And I can store up the current in a Leyden jar, or in this modern-day version of the Leyden jar, in a capacitor. So what I'll do is, first of all, disconnect the motor from the battery for the moment, and instead connect the Leyden jar, or capacitor, to the battery. Now, it'll take a while, but as time goes on, these will charge up, and eventually the voltmeter will reach the reading that it had before. And when that happens, I'll be able to run the motor from the lemon. Now, that will take a while, so we may as well go on with the story that we want to tell today, which is how the electric battery actually works.
The electric battery. It's been around since the 1800s. In many containers and under a variety of circumstances. But how does it actually work? Or not work, as the case may be. En route to the answer, and this is true with any hot topic in science, part of the fun is getting there. And to understand how a battery really works, one way to get started is to make a metal from scratch.
Begin with a single positive ion. That's an atom missing just one electron. Because it has a positive charge, it creates the potential energy of attraction, as shown here on the graph, for the missing electron. Then place more ions, side by side, one next to another. Add just enough electrons to make an electrically neutral system. Then arrange them in an orderly lattice to create a piece of metal.
An imaginary test charge would detect no change in potential energy and therefore no force anywhere inside or outside the metal. But a real electron inside the metal is acted on by all the ions and all the electrons except for itself, leaving itself a net potential energy. If that electron is moved from one part of the metal to another, the other electrons flow around to replace it, so that it has the same potential energy everywhere. That means there's virtually no force to prevent an electron from moving freely through the metal. But beyond the surface of the metal, there are no more ions and other electrons to help balance forces. So, to push an electron out of the metal requires a powerful force, creating a real electric potential and leaving a net positive charge on the metal. So the overall potential energy of a real electron drops sharply at the metal surface to a lower value that's the same everywhere inside. The electrons of a metal also have kinetic energy, but not enough to escape. The amount of extra energy an electron would need to escape from a metal is known as the work function. Alessandro Volta came along before anyone was able to construct an electric battery, much less see the inner workings of a metal. But Volta did have a knowledge of metals, their properties, and how they work. And in that regard, Alessandro Volta was considerably ahead of his time. Science was Volta's gift, and he wanted to share it with the world. In 1775, he wrote to a friend in England, describing a recent invention which he called Electrophoro Perpetuo, or the perpetual reservoir of electricity. It later became known as the electrophorus. Once charged, the electrophorus retained an unlimited number of induced charges. It was indeed a perpetual reservoir of electricity, because the charges remained no matter how often the device was touched. The scientific community hailed Volta's achievement. And in England, Joseph Priestley called it the most significant invention since the Leyden jar. While the invention of the electrophorus gave science an opportunity to advance, it provided its inventor the opportunity to visit some of the countries he'd only known about through correspondence. In Holland, for example, Volta studied Martinus van Marum's famous electrical machine. And in France, he was accepted by the avant-garde in both science and the arts. Paris was the city of Pierre-Simon Laplace, astronomer and mathematical physicist, and the great chemist, Antoine Lavoisier. And it was also on a visit to Paris that the colonial printer turned electrician Benjamin Franklin entertained Volta at dinner. Volta arrived in Paris in 1781, and during his stay, he accomplished much in the way of science. In fact, in the words of one Parisian admirer, Volta was hailed as the Newton of electricity. And so it was only natural that he visit the English universities before returning home to Italy. As a scientific celebrity and professor of experimental physics at the University of Pavia, at the age of 46, Volta might have rested on his well-deserved laurels. However, Volta happened to receive a timely letter from one Luigi Galvani. Galvani lived in Bologna, and like Volta, he was an Italian given to bold ideas and shocking discoveries. Perhaps the boldest and most shocking was an idea Galvani called animal electricity. This was a vital force, wrote Galvani, different from ordinary electricity, and it could be found in the tissue of a frog. Then as now, an electric impulse causes a frog's leg to twitch. In other words, when the thigh nerve of a freshly dissected frog is given a small electric impulse, a muscle contraction occurs. By observing the twitching of a severed frog's leg, Galvani had discovered that those nerve impulses which excite muscles into action are really electrical signals. And those signals, he said, travel everywhere throughout the body. But Galvani believed that it was animal electricity stored in the frog's nerve, like ordinary electricity stored in a Leyden jar. He thought that a discharge of animal electricity made the muscle move. But Volta viewed Galvani's discovery quite differently. Rather than detecting so-called animal electricity in all parts of the body, Volta found the impulse only in the frog's leg. And he reasoned that animal electricity was ordinary electricity, merely a jolt that was generated when two metals in Galvani's circuit happened to come into contact. Even today, there's a very significant question at the heart of Volta's argument. Why is an electric impulse created when one metal touches another? Each metal, zinc for example, has a work function that keeps its electrons from escaping. But a different metal, say copper, has a different work function. These differ by the equivalent of about 1 volt of electric potential. When two metals are brought into contact, the barrier at the interface vanishes, and electrons are free to flow into the metal where they have lower total energy. As electrons flow, the metal they leave becomes positively charged, and the one they enter becomes negatively charged, creating an electrostatic potential difference that finally balances the energy difference. Then the flow stops. If the two metals are now separated, each has a net electric charge, and an electrostatic potential difference exists between them. Of course, since the electron hadn't been discovered in Volta's day, he would have to base his argument on different grounds. So he invented the voltaic pile, which resembled an electric eel. His intention may have been to shock Galvani. But in any event, one reason the eel produces electricity is because a certain amount of moisture flows between its fin discs and acts as an electrolyte, which is a fluid containing positive and negative ions in solution.
Suppose two different metals, electrically charged by contact, are placed in an electrolyte. The metal that has extra electrons attracts positive ions from the solution. Whenever positive ions touch the surface, they can extract excess electrons from the metal. Meanwhile, the other metal, which lacks electrons, attracts negative ions. When negative ions reach the surface, the missing electrons can be replaced. So, the electrolyte tends to drive the metals back to an electrically neutral condition. If they were to make direct contact again, a new surge of electrons would flow because of their difference in work functions. But now, because of the electrolyte, the surge doesn't stop. Electrons keep flowing from one metal to the other, and they're continuously replaced by the ions in the solution until all the chemical energy in the solution has been used up.
But until that happens, a battery sheds light on both physics and chemistry. Chemical reactions at the interface between the electrolyte and one metal provide extra electrons ready to flow. At the point where one metal contacts another, the difference in energy of electrons inside each drives electrons along. Through the electric circuit and back into the solution, where they complete the chemical reaction. And so it goes, chemical energy turning into electrical energy until the chemicals are used up and the battery is dead. That's the theory behind Volta's invention, and to a certain extent, the reason why the electric battery and the electric eel work the same way. So to duplicate nature and prove Galvani wrong about animal electricity, Volta built layers of fins that were separated by a kind of electrolyte. In this case, alternating plates of silver and zinc, separated by moistened pasteboard. As with the eel, here too it was the moisture that did the trick of acting as an electrolyte. And as with the electrophorus, this invention was hailed as a tremendous success. For example, Napoleon Bonaparte, an emperor always interested in current events, hailed Volta's invention as the greatest of all time. And while that's strictly a matter of opinion, there's no question that Volta had developed the world's first electric battery. Past or present, two pieces of different metal in an electrolytic solution are the makings of an electric battery. However, to make an efficient practical battery, a little more is needed. In fact, things have come a long way from the days when Volta made stacks of different metals separated by pieces of moist cloth, clay, wood, and skin. Today, for example, furnaces melt heavy lead bars. Then, the lead is cast into grids or plates that will serve as electrodes. Here, the plates are coated with a mud paste, a mixture of lead oxide, acid, and water. Filler is added to the batch of mud that goes on the negative plates. Then the plates are assembled, alternating positive and negative with a fiberglass mat in between each pair. The plates are welded to contacts, placed inside a plastic case, and secured. The cases are filled with a solution of sulfuric acid. And finally, inside their case, the lead plates and the surrounding electrolyte are transformed, at last, into electric batteries. But if both electrodes are made of the same material, that is, if both electrodes are lead rather than, say, zinc and copper, how can these batteries work? The answer was provided by a French scientist named Raymond Planté, who discovered this new way of making a battery. He put two electrodes of the same metal, lead, into an electrolyte, a weak solution of sulfuric acid. Then he applied a voltage between the electrodes, driving electric current through the solution. This had the effect of oxidizing one electrode, changing its work function. After that, The principle's the same as Volta's pile, but this battery had a great advantage. It was reversible. Once charged, it was ready for use. Once used and discharged, it could be charged up again. That's the basic idea behind the modern lead-acid battery, the battery of the automobile. Of course, there's a lot more to today's automobile than a battery, but that's just what it takes nonetheless to get those complex machines started. So drivers around the world owe a great deal to Alessandro Volta, whether they're blessed with the cream puff or cursed with a lemon.
Alessandro Volta's father was one of 4 brothers, all 4 of whom were priests. This was not very promising for the future of the family, and so after 11 years in the priesthood, he quit to propagate the family name. And you can see that he did a very good job of it because we're still using it. He produced 6 children, 3 priests, 2 nuns, and Alessandro. This was a very effective Italian method of birth control. Alessandro, however, was not cut out for the priestly calling. A colleague of his named Lichtenberg said of him that Alessandro understood electricity, the electricity of women. Speaking of electricity, I think the time has come that we can run our electric motor because we've gathered enough charge from the lemon battery. All I have to do is to connect the motor to the capacitors like this, and when I throw the switch, we should have it. Are you ready for it? Here we go. And there it is, lemon power. Well, there's just no way in the world I'm ever going to top that. So we'll take this up again next time.
For information on this program and others in the Annenberg CPB collection, call 1-800-LEARNER.
Major funding for Ethics in America was provided by the Annenberg CPB Project